Hi, welcome to the first episode of The Manic Engineer. My name is Francois, and today we'll be printing a 3D printing pulley, timing belt pulley, as well as a timing belt puller to easily get it off the shaft and some other related work to get my garage door working again. So please join me and let's get started. I'm now in the garage and what we have here is the mechanism that opens the door. So what I will do is just to open this lid to show the internals of the mechanism. Inside this casing is the electric motor. It drives a timing belt pulley, which in turn drives this larger pulley with this timing belt. And this larger pulley is connected with a lead screw inside this track. And once that turns, it drives the nut up and down here, which is connected to this bracket. So an easy way to show how a lead screw works is using this method of the drill. And this is a nut that can easily turn on the screw. And by holding the nut so that it doesn't turn and by activating the drill, you'll see that this nut just moves left or right depending on the rotation. So that's in the one direction, closing the garage door, and this is the other direction, opening it again. This is the timing belt pulley that failed. Taking off the timing belt, we can see that the pulley melted away on the one side due to the slipping belt. This is what the gear looked like after hacking it off the shaft. And unfortunately, I did not count the number of teeth, which was really stupid. Okay, I agree, it was really stupid not to take the number of teeth before I started hacking the gear off. So what I will do is to quickly jump on Mathcad and do a calculation, because I've got the center distance, I've got the belt info, I've got the one pulley info, so it will be possible to calculate. In one of the technical manuals on the net regarding timing belts and pulleys, we find the center distance formulas for pulleys and sprockets. Here's a little picture indicating all the parameters, and further down we get three equations that needs to be solved to determine the center distance as a function of all the other parameters. With the equations now inserted in a program called Mathcad, we can solve for the center distance as a function of all the other parameters of the belt and the pulleys. At this point in time, the number of teeth on the small sprocket is 14. That gives me a center distance of 93 millimeters. If I change this to 16, the center distance changes to 91 millimeters. So there's a difference in center distance of 2 millimeters with a change in sprocket teeth from 14 to 16. I measured the play in the larger sprocket, and it was in the order of 2 millimeters. So I cannot calculate more accurately what the number of teeth should be on the smaller pulley. So the decision is here to print the pulley with a small number of teeth, and if it doesn't fit, we up the teeth until it fits. The marking on the belt indicated 170 XL 050, which means the belt is 17 inches long and 0.5 inches wide. As a check, the pitch circle diameters in CAD were drawn as shown with the calculated center distance and the two pulleys connected and the length of the belt checked. The length is confirmed as 17 inches or 431.8 millimeters as shown. To model the pulley in CAD for 3D printing, we need the belt geometry. The XL indicates it is an extra light belt. That means the pitch is 1/5 of an inch or 5.08 millimeters with the other geometric parameters as shown. In CAD, we create a sketch on a flat plane with a mirror image of the belt but only for one tooth. The sketch is then extruded as shown to a distance slightly bigger than 1/2 inch, which is the width of the belt. This extrusion is then copied around the center by the number of teeth, in this case 14. A flange, a center hole, and a hole for the spring pin can be added. The CAD file is imported into Simplify 3D, which is a slicer program to prepare the print for the 3D printer. Here we specify a few important printing parameters. The material type is petg, the same plastic that Coke bottles are made with. The height of each layer is 0.32 millimeters. The nozzle is heated to 235 degrees Celsius and it lays a single line of plastic on each layer. Once a layer is finished, the nozzle increases in height with 0.32 millimeters and printing the next layer. This keeps on going until all the layers are finished printing. Zooming in on the top left corner, we find the estimated printing parameters: 35 minutes, weight 14 grams, and a material cost of less than 6 rands, which equates to about 33 American cents. And this is the 3D printed part. A hole for the shaft, and another hole for the spring pin to transfer the torque. Now with this 14-tooth pulley printed, I fitted it on the shaft, and the timing belt pulley was way too loose and impossible to tighten with the adjustment screws provided on the mechanism. So wrong number. It must be a 15 or a 16-tooth pulley. When I wanted to remove it from the shaft, however, it wouldn't budge as the fit was a bit tight. But this time I was not going to hack it off with a hacksaw, and I rather opted to design and quickly print a puller. Shown here again the 3D pulley model, and around it in yellow is one half of the puller and a ring to keep the two halves together. Exported and printed it, and an hour later I had the puller to pull off the stuck pulley. While the new two pulleys and puller were being printed, it was time to prepare the M6 bolt and turn the ring on the mini lathe. To use this M6 bolt in the puller, I'm going to create a sharp point here, as well as also cut off the head so that I can put it in the chuck of the drill. What I'll do first is to put it in the chuck to cut the head off, put it in forward, to rotate the tool a little bit to part it off. Just clean up the edge here. I'll just clean off the thread at the end of the screw. Okay, so that's good enough for me to put that in the drill chuck. Let's turn it around and sharpen the edge. I'm going to put it in reverse and cut on the outside. Stop it, turn it around, and just use the file to clean it up. That will do it. So this part will go into the chuck. And now I can use this to pull the gear off the shaft. This is a demonstration of how the puller works. The puller consists of two halves that were 3D printed, an aluminium ring, an M6 bolt, and an M6 nut inside here. I'm going to take this apart. I'm going to use this bolt to pull off the ring like that, and then inside the two halves is an embedded nut for the screw to go through and push against the end of the shaft. This represents the electric motor shaft. At the end of the shaft it's got a center hole, and which the M6 bolt pushes against and inside. I'm going to put this on the chuck just to demonstrate how it works. Then add timing belt pulley. First thing you do is you put the 1/2 over the flange of the timing belt pulley. Then add the other one, like that. Put the ring over it. And now one can put this screw in there, turn it through the nut against the shaft, and then it's going to pull it. Instead of using this bolt, I'm going to use a bolt that I turned and put in the chuck of the drill. So now it starts pushing against the shaft, pulling it off and then wiggling it out like that. With both pulleys and the puller printed, it's time to pull off the stuck pulley and fit the correct pulley. The guy that previously repaired the garage door phoned back and confirmed that the pulley should have 16 teeth. So to put the belt on, you start by putting it on the smaller pulley, and you just turn this larger pulley in this direction and it will climb up the larger pulley easily. So now that we have installed everything, let's see if it works. Perfection! Okay, one thing that I'm not happy with is that there's axial movement on the larger pulley once I start the electric motor. So you can see it move after a second or two. Let's do it to the other side. There are 2 screws on either side of the bearing block as indicated on the manufacturing installation manual. All 4 the screws were loose, this probably due to vibration and resulting in axial play of the lead screw. These were tightened and stopped the axial movement completely. Let's do the conclusion. Large bearing block pulley was loose. The screws were tightened by adding Loctite, which removed the large movement in the axial direction. The screws were adjusted to apply the proper tension to the timing belt. The guy that charged me an arm and a leg every time for a call out the last few years is going to make less of me. I'm happy, he's not. He wanted 200 Rand for a new pulley, mine was 6 Rand. He wanted 800 Rand for the call out, which now I can use for a few bottles of brandy during COVID, but only when Cyril lifts the ban again. I got to design something and got my hands dirty and do some work on my 3D printer, mini lathe and minimal. Well, this was the first episode. I hope you liked it. Like and subscribe. If you want to see anything else, please let me know in the comments. If you want any information about the programs I used, please let me know. Thank you and see you in the next episode. Francois, the Manic Engineer. Cheers.